9.5 Lesson 3, Part B, Extra Examples and the Proof of Theorem, 9.16. So in Part A, we looked at an example to examine the relationship between a series and its corresponding absolute value series, and we used that example to take a look at Theorem 9.16 about absolute convergence, and we also used that example to understand the definition of an absolutely convergent series. And then we looked at a different example to look at the definition of a conditionally convergent series. So now we'll look at some extra examples for absolutely convergent series and conditionally convergent series. And we will also take a look at the proof of Theorem 9.16 at the end. So here we look at example 5a. The instructions are determine whether each of the series is convergent or divergent. So we want to know if this series converges or diverges, and if it converges, we want to classify it as either absolutely convergent or conditionally convergent. So in part A of the lesson, we looked at Theorem 9.16, which states that for a given series, if the corresponding absolute value series converges, then the sign series also converges. And we would say by definition that the sign series is absolutely convergent because its corresponding absolute value series converges. On the other hand, you could have the corresponding absolute value series diverge, but the sign series converges. If that's the case, we say the sign series is conditionally convergent. So let's take a look at example 5a here. And if you look at a sub n here, and you take the limit of a sub n as n goes to infinity, one thing that you need to know is that when you look at n factorial and compare it to 2 to the n, two to the n is an exponential function, but n factorial has a much faster rate of increase than exponential functions. And because of this, the numerator will increase much faster than the denominator. So as n goes to infinity, the limit here is infinity. More significantly, it's not equal to 0. So by the nth term test for divergence, we know that this particular series in example 5a will diverge. Example 5b, determine whether each of the series is convergent or divergent. Classify any convergent series as absolutely or conditionally convergent. So when you look at example 5b, you recognize the series to be an alternating series. And it's pretty easy to show that this alternating series converges by the alternating series test. But what we can do is we can skip that for now and consider the corresponding absolute value series. And we can determine if this corresponding absolute value series converges or diverges. If it converges, then we can use Theorem 9.16 to conclude that the original series must also converge. And we would know that the original sign series is absolutely convergent. However, if it diverges, then we may have conditional convergence, so we would have to check for conditional convergence. So when you look at the corresponding absolute value series, the a sub n part is always going to be positive. It is the negative 1 to the n that could give us negative terms. But because we have absolute value, we won't have negative terms anymore. So you can simplify the notation for the absolute value, the corresponding absolute value series, by getting rid of the negative 1 to the n and the absolute value signs, because this is all the terms here are going to be positive, so we don't need to worry about the absolute value anymore. You would recognize this series to be a p series with p equal to 1/2, and therefore it will diverge. So the corresponding absolute value series diverges. But we could have conditional convergence. We know that the corresponding absolute value series diverges, but if we can show that the sine series converges, then we would have conditionally convergent for this series. So we're going to use the alternating series test. In the first example that we looked at in this video, I didn't have to do this process because the sine series itself was shown to be divergent using the nth term test for divergence. So we used the alternating series test to show that the original sine series is in fact convergent by the alternating series test. So we check for the two conditions. The limit of a sub n as n goes to infinity is 0, and a sub n plus 1 is less than or equal to a sub n for all n. That's true because if you look at the numerators here, they're the same. So the fraction with the larger denominator will be smaller. So we may conclude that the original sine series is conditionally convergent because we saw that the corresponding absolute value series diverges. So by this definition of a conditionally convergent series, we know that the series from 5b is conditionally convergent. So in this example, we have the same instructions. We want to know if we have a series that either diverges, or if it converges, is it absolutely convergent or conditionally convergent? One thing that you'll note is that although we have negative 1 raised to some power, it's not n or n plus 1, and what you have here is such that you will not have an alternating series. You don't have opposite signs for every pair of consecutive terms. So this is not an alternating series, so you cannot use the alternating series test. So how would you determine if this signed series converges or not? As we saw with the first example from part A of the lesson, sometimes it's easier to consider the corresponding absolute value series. So let's look at the corresponding absolute value series here. And of course, we can simplify the notation for the nth term, because whether a term from the original sine series is positive or negative is determined by this part of the description. So if we have absolute value, all of the terms must be positive. So we can get rid of this, and we can also get rid of the absolute value sign, because 1 over 3 to the n for n greater than or equal to 1 will be positive. So now we have the simplified notation for the corresponding absolute value series, and you would recognize this to be a geometric series where a is equal to 1 and the common ratio would be 1/3, because you have 1 in the numerator, which you can write as 1 to the n power. It would be 1 for any value of n greater than or equal to 1. So for that reason, we know that the corresponding absolute value series is a geometric series whose common ratio r is, of course, 1/3, and the absolute value of 1/3 is 1/3, and that's between 0 and 1. So we know that the corresponding absolute value series converges. So using Theorem 9.16, because the corresponding absolute value series converges, the original sine series must also converge, and therefore by definition we say that the original sine series is absolutely convergent because its corresponding absolute value series converges. So now we look at example 6b. Does this alternating series converge or diverge? We can examine the answer to that question by using the alternating series test. But let's not do that right now. Let's begin by considering the corresponding absolute value series, because if we have a corresponding absolute value series that converges, then we don't have to do any work for the original sine series, because by Theorem 9.16 it must converge. So we can save some work But if the corresponding absolute value series diverges, then we do have to go back to the original sign series and see if it converges, because it might be conditionally convergent. So let's begin by looking at the corresponding absolute value series. So what we know is that because for n greater than or equal to 1, natural log of n plus 1 will be positive. In the original sign series, only the negative 1 to the n would have given us negative terms. The a sub n part was always positive. So when we have the corresponding absolute value series, the absolute value will negate the negative 1 to the n because all of the terms must be positive. So you can simplify the notation for the nth term in the corresponding absolute value series by getting rid of both the negative 1 to the n and the absolute value signs. So we have this series, which of course has positive terms, and you want to think about whether this converges or diverges. So what we can do to show that the corresponding absolute value series diverges is by doing the direct comparison test, where our comparison series would be the harmonic series, a p series with p is equal to 1, and therefore it diverges. Now we can demonstrate that the nth term we can demonstrate that the nth term of this series must be greater than or equal to the nth term of the divergent p series. And therefore, by the direct comparison test, this series, which can be shown to have larger terms than corresponding terms of the divergent comparison series, must be also divergent by the direct comparison test. And we state that as our conclusion here. This series here diverges by direct comparison to the divergent p series. And of course, this relationship has to be true. The numerators are equal, so the fraction with the larger denominator must be smaller than the fraction with the smaller denominator. And it can be shown that for all n greater than or equal to 1, natural log of n plus 1 is less than n. And because of that, the denominator here is smaller, so the fraction is larger. So at this point, we've shown that the corresponding absolute value series diverges. So we cannot apply Theorem 9.16 because the corresponding absolute value series diverges. However, it is possible that the original sign series might converge. And if it does, we would have conditional convergence, because if we can show that the original sign series is convergent while the corresponding absolute value series is divergent, that means the original sign series is conditionally convergent. And we can show that the original series converges by using the alternating series test. So when we look at the alternating series test, we check for these two conditions. The limit of a sub n as n goes to infinity is 0. And then you can verify that a sub n plus 1 is less than or equal to a sub n for all n. And that is true because the fraction with the larger denominator will be smaller than the fraction with the smaller denominator. So by the alternating series test, our original sign series converges. But we saw earlier that the corresponding absolute value series diverges. So what we have is conditional convergence. Our original sign series is conditionally convergent because it converges by the alternating series test, while the corresponding absolute value series diverges. We'll be using Theorem 9.7 to help us prove Theorem 9.16. So in Theorem 9.7, we learned about properties of infinite series. So if we know that a particular series converges to some sum A, and another series converges to some sum B, and C is a real number, then the following series converge to the indicated sums. So if you have a constant multiple of a convergent series, then that series must also converge to the constant multiple times the sum of the original series that was known to be convergent. Now, if you take two convergent series and you add them together, the sum of the two convergent series must also be a convergent series. And the difference of two convergent series must also be a convergent series. So we're going to use that in our proof of Theorem 9.16. Theorem 9.16 states that if we have the corresponding absolute value series known to be convergent, this is called the hypothesis of the theorem. So in proving the theorem, we assume that the corresponding absolute value series converges, and based on that assumption, we want to show that the signed series also converges. And we're going to use Theorem 9.7 to help us do that. It may be easier for you to understand the proof by looking at it from the end of it and then going back to the beginning. If you look at the end of the proof, you can see that we're saying something about the series that we're trying to show converges. And we are saying that the series that we're trying to argue must converge can be written as a difference of two other series. And if we can show that these two other series must converge, then by Theorem 9.7, the series that we're trying to prove converges must also converge. So that's why we want to begin by considering the two series that we have on the right side of this equation. There's one here, and this one is, of course, we assume that absolute value series to converge by hypothesis. So at the beginning of the proof, we're trying to show that this series converges. And we're going to show that this particular series converges by doing the direct comparison test. So we have to compare the nth term of the series that we're considering to the nth term of a series that is known to converge. And of course, this series here is known to converge by hypothesis. So we want to compare the nth term of this series to the nth term of a series that is known to converge. So one observation that we can make is stated in the very first line of the proof. If you have a term and you add to it the absolute value of that, either your term was positive to begin with, and if that's the case, if you add the absolute value of that term, you'll get something that's twice as large. Or your term was negative to begin with, and if you add the absolute value of that term, then you'll get 0. So this is putting a bound on what the nth term of this series can be. It can either be 0, or it could be 2 times the absolute value of a sub n. And if you look at that and you think about the direct comparison test, here's what we can conclude. By hypothesis, we know that the corresponding, the absolute value series converges. By hypothesis, we have that the absolute value series converges. So this is a constant multiple of a convergent series. So by Theorem 9.7, this one converges. So what we're saying is now take a look at the nth terms of the two corresponding series. So we can show that because the nth term of this series is either less than or equal to the corresponding nth term of the convergent series, it must converge by direct comparison. And now that we have that, we know that this series converges. And of course, this one here converges by hypothesis. This particular line in the proof establishes a relationship between the nth term of the series that we're trying to prove converges and the nth terms of these two series that we now know to be convergent. So you can write a sub n as the difference of a sub n plus the absolute value of a sub n, which is the nth term of this series known to converge, and the absolute value of a sub n, which is the nth term of this series, which is known to converge by hypothesis. And when you subtract the two, you get a sub n. So we can establish this relationship, and by Theorem 9.7, because this two series on the right converge, the series on the left must converge. So we have shown that this series must converge by assuming the convergence of the corresponding absolute value series and doing some logical reasoning. In part B of lesson 3, we looked at extra examples and the proof of Theorem 9.16.